As Nina said, my name is Eric. I work at the Center for Bionic Medicine in what is now the Shirley Ryan AbilityLab. Formerly, it was known as the Rehabilitation Institute of Chicago. We had a name change just about a year ago now, like 11 months back in March. But I'm also a Ph.D. student at Northwestern University in biomedical engineering, so I'm kind of halfway in between those two. The Center for Bionic Medicine is a large group of researchers and engineers and clinicians, and we kind of comprise three different labs. We have neural engineering for prosthetics and orthotics. That's the lab that I'm in, and that's the lab that is directed by this is my advisor, Levi Hargrove. Don't tell him that I forgot his name. We also have the Maxinator Center for Rehab Technologies and Outcomes. That's led by Arun Jayaraman. And we have the Neurobionics Lab, which actually focuses a little bit more on designing prosthetic devices. That lab has actually since moved to the University of Michigan. So we're a little sad about that, but we still hold on to some of the grad students and we still do some of that work and we collaborate a lot with them. But like I said, the CBM is a big interdisciplinary group of students and engineers and therapists and clinicians. There's a lot of us that all work here, all kind of like pulling our different expertises together into this one problem. The engineers by themselves don't know what they're doing, or they don't know why they're doing it. The clinicians don't know how to build things. You kind of have to get this large group together. If you look closely at this picture though, there is one thing that you'll notice is missing, and that's me. I was seriously gone, like I was 5 minutes, I was gone. And in those 5 minutes that I was gone from the lab, they got everybody together, posed them, organized them, took the photo, and everybody went back to their desks before I had any idea what happened. I don't know if they were trying to like tell me something or what, but I should be in there. I'm not an imposter, I promise. But what do we do? What is, why do we think about prosthetics? This is, why is this interesting? I shouldn't have to explain why this is interesting, but I'm going to because I have to defend my nerd status here. Prosthetics in history, prosthetics in popular culture, we have been thinking about replacing our limbs with artificial limbs for well over 9,000 years now. Vishpala from the Hindu story of the Rig Veda, that was 7,000 BC when that story happened. This was a woman who lost her foot and she was granted a foot of iron by the gods. You also have the Nudwa, Ergilamva. That was not right. Anyway, that one's Celtic. And then you have Tezcatlipoca, which was an Aztec deity, 1300 AD. You have all of these mythological kind of limbs being granted from the gods for those who have lost their limbs. In more historical terms, we even have examples all the way back to the 2nd century BC. We had Marcus Sergius, who was a general, Roman general during the Second Punic War. We don't have photos of him, sadly. But you'll notice on this coin here, you'll notice that he's actually like kind of striking with his sword, but he's holding it with his left hand. That's because he lost his right hand in a battle. And he had an artificial right hand made for him on which he mounted his shield. So he was actually like kind of doing backwards, which was very atypical for that time. Pirates, always amputees for some reason. You have Barbarossa, who was a Turkish pirate, and then you had Francois Leclerc, who was a privateer. He was the first person to have like the peg leg. Barbarossa lost his left hand in a battle against the Spanish, and he was replaced with a silver arm entirely, which is kind of where the idea of that hook comes from. In popular culture, again, like I said, it's pirates. It's always pirates. I don't know why it's always pirates, but it's always pirates. Whenever I'm doing demos with little kids and I see this, the parents are always just like, "Oh, look, a pirate." And I'm like, I mean, I'm not going to say no, but... But yeah, we have prosthetics in all this popular culture. We have literature, we have movies, there's the Luke Skywalker hand, told you. RoboCop, we've got, what do we got? The prosthetics from Star Trek, we have, and Full Metal Alchemist fans? Yeah, that one guy. Video games, Deus Ex, a lot of others. You know, it's fun to think about, and we can't stop thinking about like how would we do it, and people get excited about it. If anybody is a big fan of TED Talks, there's actually an entire section on their website for prosthetic limbs. On the bottom left, you'll see Todd Kuiken. He is the director emeritus of the Center for Bionic Medicine, and that talk is well worth watching. But I want to point out this one here by Hugh Hare, who's the director of a prosthetics lab at MIT. And what they did here is that the woman here on the left, she was a runner in the Boston Marathon, and she lost her leg during that Boston Marathon bombing in 2013. She got brought in by the MIT Media Lab to develop and to give her a prosthetic ankle that would allow her to dance again, since she was a dancer. And the TED Talk is beautiful because she comes out on stage and she performs an entire dance with this bionic ankle. It's really, really fascinating. And the leader behind the lab, like I said, Hugh Hare, he is also a bilateral amputee. He lost his limbs while he was rock climbing. And he's interesting for a couple of reasons. One, he's the only guy that I can know who can pull off the suit jacket and shorts combo. I've tried it a couple times and it never works quite as well for me. He also cheats at rock climbing. But even so, he has this great story where when he was teaching in class at the beginning of the semester, he had his legs set at one height. And every time that he came back into class, he added an inch. And he just kept going until somebody said something. And he was like 6'7" by the time someone was just like, hang on a minute, you're not the same height as when you started. So it's, you know, prosthetics is everywhere. We see it in all of our media, we see it on the internet, we see it in news, we see it in science. What do we still have to do? What is the challenge? And I'm going to break it down into two separate sections. The first challenge is actually not a little bit of a challenge, so you'll have to bear with me for a second, but the first challenge is that people are incredible. People are capable of adapting to all sorts of circumstances. On the top right is Josh Sundquist, who you might remember from that Facebook post that you saw of the guy as all of the Halloween costumes. No? Okay. Moving on. He does a lot of this stuff. You know, the video there, he was as Tigger. He's also done, he was a flamingo. He did an IHOP sign, which there's a pun in there, which he was going for probably. Anyone recognize the guy on the top left?
Disney?
That is, do I remember his name? Django Reinhardt, the gypsy guitarist. He is a guitarist, but he lost the use of his two fingers in a fire a long time ago. And he was told he wasn't going to play guitar again, but what he did was he developed an entire chord structure that he could play on guitar using only two fingers, and that sound defined an entire generation of jazz. So people are incredible in their way to adapt to circumstances, and I think a really great way of illustrating that is with this video from the 2016 Paralympics. It was shown on BBC Channel 4 to advertise the Paralympics, so I'll just play like a minute or so.
Yes, I can, suddenly, yes, I can. Gee, I'm afraid to go on has turned into, yes, I can. Take a look, what do you see? 133 pounds of confidence in me. Got the feeling I can do anything, yes, I can. Something that sings in my blood is telling me, yes, I can. I was just born today, I can go all the way, yes, I can.
So you should definitely look this up on your own. It's only 4 minutes long, well worth the watch. It's called, it's called We the Superhumans. And like I said, it does a great job of showing that you can have what some might consider a disability, but not be disabled. You can find ways around that and not be limited by that. So the reason I bring this up as a challenge is because we have to build things that are better than people can adapt on their own. And that's actually surprisingly hard. If you give somebody a device that helps them complete something normally, but they have a way to do it that they adapted to themselves, that lets them do it faster and easier, a lot of people don't care so much about normal, they care about efficient. Like I could spend a whole bunch of time trying to get this thing to, pick up this water bottle and open the cap, or I could just buy something that doesn't have a cap on it, problem solved. So that's the first challenge, is just that people are able to adapt and people are incredible in the things that they're able to do. The second challenge is this. This is what we're trying to replace. I didn't memorize all the muscles, but there's a lot of them. There are a ton of muscles in the human body. There are 600 muscles, approximately, in the human body. We're going to do a little bit of math here, so I hope some people here like math. Let's assume that these muscles can either be contracting or not contracting, on or off. There are this many possible combinations of muscle activations that you are capable of performing. Anybody have a ballpark idea of what that is in not binary terms? All right. It's huge. 4 times 10 to the 180th power. So that's kind of like an astronomically large number. So let's compare that to another astronomically large number of the number of atoms that are in the observable universe. Anyone have an idea? 1 times 10 to the 82nd. So you're off by a factor of 10 to the 100 power. You're off by a Google. Which you look at that and you're like, yeah, that's a big number. But I'm going to continue to hammer this point home until you're sick of it. Let's write out these numbers in all of their digits. We have run out of atoms in the universe. And now we've run out of muscle combinations. So that's the complexity that we're trying to deal with. These are all of the possible muscle combinations that you could do, all the possible muscle contractions that you could be pulling at any given time. So to try and figure out what a person wants to do is really, really difficult. Hands are complicated. We use our hands all the time. Hands have worked their way into everything that we see around us. They've created everything that we see. They've worked their way into our language. When you say, can you please hand me something, or can you hand me in your homework, or can you give me a hand? Hands are so important that they've worked their way into the English language. There are 29 muscles that control all of the individual movements in your finger, all 15 different individual separatable movements that you can do in your hands. And they let you do things like this. Right? And I love that kid in the background that's just freaking out. It's just, oh my gosh. Hands are amazingly complicated. Trying to get a prosthetic device to do this, to figure out exactly what somebody wants to do, when they want to do it, as fast as they want to do it, as accurately as they want to do it, is an incredibly, incredibly, incredibly challenging task. I want you to kind of take a look at these images and just think about what they represent to you. These kind of things that you do every single day that you don't think about. They've become routine. I want you to think about all of the hidden complexity that actually makes up these tasks. Brushing your teeth, for example. You have to find the toothbrush, you have to find the toothpaste, you have to squeeze the toothpaste, but not obliterate the toothpaste onto your toothbrush. You have to take the toothbrush and find your mouth without hitting anything else in your face. there's a lot of things that you don't think about. It's just perfectly normal. But when you're trying to replace that function, all of a sudden you have to start thinking about things in a different way. You're all probably like, all right, I get it. But I think it's important to think about these things. These are the types of tasks that we're trying to get prosthetic devices to do, not necessarily help people stack cups in 5 seconds. These are what we kind of call activities of daily living. These are like the basic necessities that somebody needs to be able to perform their, to go about their day-to-day lives. Things like dressing themselves, feeding themselves, getting to work, doing work, all of that kind of stuff. So these are the types of tasks that we focus on when we're making prosthetic devices. So what are the current prostheses that are available? The cool toys that I brought. We're going to start with just cosmetic devices. This is maybe not the most basic device, but it's the, I'll say, least functional device. It doesn't have any moving parts. It doesn't have any motors. It doesn't have any joints. It's just a silicone thing that looks like the limb. And it looks a lot like the limb. Like if I covered up half of that, the slide, you'd be like, that's a person. I don't know why this is on the slide. These are incredibly realistic looking. And for some people, that's all that they need, especially if you're talking about somebody who is, for example, a unilateral amputee, somebody who's only missing like one hand, for example. If I still have one perfectly functioning hand, I can do most of the things I need to do throughout the day with this one hand. So maybe I just want a device that helps people not stare at me all day. It helps me look like I am more complete. It's cosmetic. And you can also use it to do things like kind of hold objects in place. If you're talking about like opening a jar of peanut butter, you can like hold the jar of peanut butter here and then use your functioning hand to open it, stuff like that. So for a lot of people, this is all that somebody needs, if that. Somebody who was born without a limb, for example, a lot of people who have congenital limb differences actually opt out of prosthetics entirely because they were born that way and they learned their entire life to do without that limb. Anything that I throw on top of that ends up being more bother than it's worth. So we have these cosmetic devices. What is the next kind of device we have? This is something that we would call a body-powered prosthetic device. That's something like what I have here. So anyone want to take a guess how old this type of device is without looking at the slide? Because the number's on the slide.
Very old.
Very old. That is the correct answer. These were developed back in the Civil War. It was first patented on the left in 1912. The patent for this device is over 100 years old. Functionally, this device works exactly the same way, like no major changes. What I have is a harness on like this. It's connected to a cable that reaches all the way out to the device. When I pull on the device, the hook opens up like that. When I release, the hook closes. And again, for a lot of people, that's all that they need. If they just need to hold something, ta-da. If you just need to like hold a device, hold something in place, this will do that. I don't even have to like constantly put force on it. It just kind of, you have these rubber bands right here that hold the device closed. So again, because a lot of people will just use their prosthetic device to stabilize something, for a lot of people, these kinds of very simple devices are all that somebody needs. There's also, you have improvements on this. This one, for example, is just made of like aluminum. You can get ones that are made out of steel. I've seen farmer's hooks, for example, that are made out of steel, and they have extra extensions off of them that allow you to like hold onto a bucket, for example, because they know that's what somebody's going to be using it for. This kind of device is relatively inexpensive. It's very durable. You can bang it around all you want and it's probably not going to break. If the cable here breaks, for example, you can literally go to a bike shop and get a bike cable, fit it in here, does the exact same thing. It's basically the same material. So it's very low cost, it's very durable, And for a lot of people, it's their preferred prosthetic device, just because of that simplicity and because of that cost factor. I'm going to try and not drop any more things. No guarantees. So we have these body power devices. But this one is it's what we would call a transradial device. It only replaces the hand. So somebody would need a little bit of forearm left over. What happens if you move a little bit higher and you're trying to replace somebody's elbow, for example? Here's where you start running into some problems, because you only have that one cable, and now it has to do a whole bunch of movements. It has to be able to flex the elbow up and down. That cable has to be able to rotate the wrist. It has to be able to maybe flex the wrist in and out like that, and also open and close that hook. And the way that you do that is kind of clever and ingenious. There's a little cycle lock on the side, and you can kind of it's almost like shifting gears a little bit against the side of your body. You kind of push it against your body, shift it into the mode that you want it to do, and then when you pull on the cable, it'll adjust that joint. So it works. Nobody would say that it's ideal. So when you get to these kind of higher level amputations, it's the complexity of the task that the complexity of what you're trying to replace is more difficult. There's more functions that are lost, and there's also there's less body to control that with. So it's this really drastic trade-off. So as you deal with prosthetic devices that are for the upper arm or for the shoulder, you start running into a lot of ingenious but non-practical solutions like this to get all of that range of motion. Lower limb devices, prosthetic legs. This is actually going to be more common than upper limb. About 90, I think about 90% of amputations are actually lower limb amputations, not upper limb amputations. And that's something important to think about, when you see news articles or things like that. Almost every time you see a prosthetic device on the news, it's like a hand. I don't know why. Hands are interesting, I guess, but that's a smaller population than the larger majority of people who need a prosthetic leg. So because I botched that transition, I'm going to play that video again. Prosthetic legs have an interesting issue. If you're talking about trying to go up and down stairs, for example, you can see the gentleman here, he has to do this sort of one step at a time thing to walk up or down a staircase. There's an advantage to trying to replace walking that you can't find with hands, for example, and that is that walking is this cyclic task. Every single step is the same, as long as you're walking on the same surface. As you start throwing in stairs like that, you have to start doing these compensatory movements. You have to kind of go up the stair 1 foot at a time and kind of trail or drag the prosthetic leg behind you, which is, again, not ideal, not insurmountable, but not particularly great. Prosthetic legs also require a lot more energy. Our body kind of serves as a little bit of a spring. With every step that you take, the tendons that are in your ankles kind of store energy, and when you walk forward, it releases that energy and kind of propels you forward a little bit. So these devices don't really have that a lot of time, so you almost have to throw your leg forward to be able to get the foot to do what you want it to, and that takes a lot of energy to do. Anyone recognize this guy? Yeah, so this is Oscar Pistorius, who is not to be confused with Jaco Pastorius. This is the first time that joke has gotten some laughter, so I appreciate that. Most people are like, I don't know who that is, and then I'm sad. Oscar Pistorius, South African runner who, I guess it was the 2016, no, it must have been earlier than that, 2012 Olympics, I think. He was trying to run in the official Olympics rather than in the Paralympics. And there was a really, really big debate about whether his prosthetic legs gave him an advantage And people kind of look at the springs and they're like, of course he was at an advantage. They're giant springs. They literally propel you forward. It turns out the answer was not quite so clean cut. Like I said, our body is also a spring. You just tend to not really think about it. I think more of the issue for his inclusion in the Olympics came down to what height he would have been. And people were arguing that his prosthetic devices made him taller than he would have been if he hadn't lost his legs. But there was a paper that was published by a whole bunch of biomechanics who were analyzing people walking on treadmills with different devices, trying to figure out like how much springiness do we have in our legs, how much springiness is in that kind of foot. And they determined that he was actually not at a disadvantage. And that's why he was allowed to participate in the official Olympics in 2012. Side note, one of the authors on that paper was Hugh Hare, the rock climbing guy from earlier. On one side, he's kind of an expert in that area, so that's good. On the other side, he's a really, really big transhumanist. So there's like a little bit of like a, not quite, what's the term I'm looking for? Like bias sort of thing. Like, but regardless, he didn't do very well in the Olympics, so it's almost kind of a moot point. He killed it in the Paralympics, though. So I think that's all the body power devices. Yes. Fortunately, robots came along and addressed some of these issues, and then also brought in more issues of their own, as robots tend to do. With any sci-fi book that you've ever read, robots solve problems and then also cause problems later on. So these are robotic hands, and the image that's on the left is actually what is inside of here. So I know this looks like it has 4 fingers. These two have nothing inside of them. It's just these 2 fingers that have that sort of metal claw inside of it like that. These devices are very simple to operate. All they do is open and close, and that's it. But you have to figure out, like, I'm going to turn this on because it takes a while to boot up for whatever reason. So you have this robotic device. You have it on the end of your hand. How do you get it to do what you want it to do? Use remote control? No, that would be incredibly silly. You have to come up with something different. So let's think about how we control our limbs. So this is a picture of my arm, my muscles. I know my shirt's not like rolled all the way up so you can't see, but trust me. Our brain sends a command down to our muscles, and then our muscles do the thing that our brain told it to. When you have an amputation, you can still send that command down to those muscles. When your muscles contract, they generate a tiny electrical signal. You can use that electrical signal to figure out what somebody wants to do. So if I record the electrical signals, calm down. When you record the electrical signals from the forearm, from the missing muscles, if I contract the muscles that are on this side of my arm, I can signify to the robot that I want the hand to close. There we go, close. If I contract the muscles that are on this side of my arm, I can signify that I want the hand to open up. And it's literally all that's happening is that there's a tiny computer or a voltage gate or something in here. You're just comparing electricity on this side, and playing a game of which is bigger. Very simple, very straightforward movement.
Is that acting just as a switch, or is there actually like a sensor that would stop it if there was something in the ground?
There is not. So thank you for bringing that up. I mean, you guys are going to be able to play with these things later. I would have said this earlier, but I'll bring it up now. Rule number 1 with the hand, don't put your hand inside of the hand, or else you will lose your hand and then you will need a hand. There was, oh gosh, I was at the Chicago Science Festival. All right. I was at the Chicago Science Festival, and some other guy had this on, and he was doing the thing, and we were talking about robotic devices. And this frail old, maybe like 50-year-old, 60-year-old woman came along and without missing a beat went, ooh, and like shoved her hand into the thing like as fast as she could. And I freaked out. I was just like, no, 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 don't do that. Because this thing can put out a lot of force. It's literally just a claw on the inside. It's 1 degree that does this movement. So it's very good at doing that one movement, and it can apply a lot of force in a small amount of time. So don't put your hand inside of it. You can put your hand inside of that one, that's fine. This has like 2 rubber bands on it. You're not gonna, this one, don't do that. All good? But yes, that is a big problem with prosthetic devices. You're skipping around in my presentation, sir. There's nothing to limit the amount of force intrinsically that happens here. You can add extra stuff. For example, you can add, you can look at the amount of current draw that's happening in the robot, and if you see the current draw go up, you can be like, oh, okay, it must be like pressing on something. It's not an ideal solution. But again, this kind of operation, very, very simple, very responsive. This works pretty much 100% of the time. I never have to worry about it like not like kind of going crazy, like RoboCop hand or something, right? Like it's gonna do what I want it to 100% of the time because that control system is so simple. There's only 2 options. It's really hard to mess that up. More things you've probably seen online. You've seen these prosthetic hands that have all the individual moving fingers, right? So on the left was a video that I took in portrait mode. Sorry about that. But it ended up fitting well on the slide anyway, so I don't feel too bad. But this was a demo at a conference that I went to, just showing off this hand kind of moving around. On the right is something called the iLimb, which is one of the first prosthetic hands to have those individual moving fingers. And the way they do that is that each of the fingers is its own robot, and you just kind of attach the finger to the hand, which is fantastic because if somebody is missing 1 or 2 fingers, instead of having to give them a whole prosthesis like that or something, you can just make them a little cast and then stick 2 robotic fingers on the end of it. Really, really cool. Side note about the iLimb. I talked to a guy who was a triple amputee from Operation Iraqi Freedom. He lost both of his legs and he lost one of his hands in an IED explosion. And he was talking about how he uses a wheelchair to get around. Because he is working with Veterans Affairs, they got him one of these prosthetic devices, the ones with all the individual moving fingers. The way he uses his wheelchair is he'll grip the wheelchair normally with his intact hand, but with his robotic hand, he'll actually kind of like, he'll punch the rim to kind of push it forward. First day with the iLimb hand, with all the individual fingers, put it on, sat down in the wheelchair, all right, I'm ready to go. Punch the fingers off of his hand, just off. Those fingers cost $10,000 a piece. He punched $40,000 of fingers off of his hand, and he never went back to that device. He uses something like that. Because again, like I said, if a lot of times, I'm not gonna drop it, a lot of times all you need is something to stabilize. You don't necessarily need something that has all the individual moving fingers. The way that he got around, he needed something that was durable. He didn't need something that had all these different grasping modes. Side tangent over. I do that a lot, I apologize. I don't apologize. So you have all of these different fingers, right? How do you control these? You can't do the same thing that you have there because I don't have enough individual like on-off muscle switches in my hand to be able to pick up without confusing it with something else. The way that it's done right now is that, again, so I actually didn't show you the inside of this. There's like these little metal domes that are on the inside here. These are what are picking up the electrical signals from my forearm whenever my muscles contract. So the way, if this had individual moving fingers and it was capable of doing all of these different like grasping patterns, 2 fingers, 1 finger, full hand, key grip on the side, something like that. The way that control scheme works is you start with just a single open close in one sort of grasping pattern. If you want to switch to something different, you'll actually contract all of your muscles at the same time. It'll recognize that and it'll go, okay, you want to do something different. And now you can do open and close with this different grasp. And if you want to switch to something different, boop, you go down again. Now you have a different grasping pattern. And if you want to do a different one, co-contract again, you go back to that pattern. And there's this like circle that you have to go through. So if I'm trying to pick up something in key and now I want to pick up something in like a pinch grip, I have to cycle through 3 different modes before I can get around to the thing that I want to. Not ideal. The other option that shows up is to do this sort of Morse code kind of thing where you can say like, all right, 1 pulse, I'm going to switch into power mode. 2 pulses, I'm going to switch into chuck grip. 3 pulses, I'm going to switch into like a key grip on the side. And if I just hold a long co-contraction, it goes into fine pinch. Also not ideal, slightly better, also not ideal. But now you have to remember like this code of like, oh, was it 2 or was it 3 or was it a long one? I don't remember. Or with that cycle, you have to remember which mode you're in and which mode you want to go to and how many times you have to cycle through to get to the thing you want. Since kind of more recently, you're starting to see, ta-da, smartphones come to the rescue for a lot of stuff. Rescue, I use that term loosely. iLim, which has made a lot of improvements on their hands since the guy punched his fingers off, they've made an app where you can actually just pull it out and say, I want to do this type of grasp, and it'll switch to that. And then again, it's that same open and close sort of thing. So now I have more options, but if I'm over here and I want to do something and now I want to go over here, I have to pull out my phone every single time, go to the iLim app, wait for it to load, maybe, click the thing, and then go put it away, right? So the robotic control is very, very difficult. We have very advanced prosthetic devices that can do a lot of things. To me, one of the big things that's holding prosthetic devices back is the control. How do you get it to do what you want, when you want it to, without doing a bunch of other stuff? This is where we came in. Segue. One of the big things that we do at the Center for Bionic Medicine is focus on control of these prosthetic devices. So again, with these, we call them MYOELECTRIC devices, myo meaning muscle, electric meaning electric. Again, as a refresher, can you command the prosthetic device directly with the brain? Kinda, sorta. There's people who do that, but it's very invasive. Like you have to do a surgery to go into the brain, to stick a chip like on the brain to get it to control the hand for a couple of years until the thing stops working, and then you have to do it again. Not ideal. Like a lot of people always ask me like, why don't you just go into the brain? It's because it's a big deal to go in, like if you can avoid it, don't go into the brain. Don't, brain surgery, last resort. Amputation is, by comparison, relatively minor compared to something like high-level quadriplegia, for example, where you have no movement of the legs, no movement of the arms. You have trouble with breathing, for example. Things like that. That's where there can be a benefit of going into the brain and doing like robot control of a limb with like a brain chip, for example. And that's where you see these things happening. But for prosthetic devices, for now, not an option. So what do? We can still send those commands down to those missing muscles. The movements that you're trying to do each have this sort of unique electrical signature that's associated with them. It looks different when my muscles are contracting like this versus when they're contracting like this, right? So if I teach a computer to recognize these, if I collect a bunch of electrical signals and I plot them here and I collect some data when somebody's not moving their arm I collect some data when they're trying to close their hand. I collect some data while they're trying to open their hand. And I take a look at it and I say, can I figure out what somebody's trying to do just by looking at where these signals go? And the answer for this extremely basic thing that I made is yes. I can kind of draw some circles around these and I say, all right, if you fall within these circles, I'm pretty sure this is the thing that you're trying to do. Kind of draw some lines separating everything out. And now we have a machine learning option where I can teach a computer to recognize the muscle contractions that I'm asking it to do. And it can figure out the differences between these different movements and do that on the fly. So what's on my next slide? Yeah. So the prosthetic device is literally trying to predict the movement that you're trying to do. And I'm going to see if this feels like cooperating. So I taught this earlier. We're going to see if it feels like remembering. Yeah, open, close. No. So this is one of the problems with this kind of approach. It works relatively well. Now you want to rotate. Okay. So it works pretty well as long as the signals are consistent. So I think a few of you might have seen this. Stop. Calm down. A few of you might have seen this. When I came in, I was doing some movements and this was recording it and trying to figure out what I wanted to do. So I taught the computer to recognize my movements and it was working better than it is now. Since then, I took this off, put it on the table, walked around a bunch. What could have changed? Maybe the electrodes are in a different location on my arm, so the electrical signals are going to be different even if I'm doing the exact same movement. This movement is similar enough that it can figure out what I'm trying to do. This movement is not, it has no idea. So what I would have to do is I'm just going to reteach it now. Is there a time limit for like how, I feel like I'm going on a whole bunch of tangents and everyone's going to be stuck here for like 7 hours. Nobody had anything they wanted to do on a Friday night, right? All right, so the prosthetic device is showing me the movements that it's trying to learn, and I'm just replicating that with my own arm. So I'm providing electrical signals to the computer to teach it what my unique muscle signature looks like when it's doing these movements. So it's just going to collect a couple of examples. A few more examples. It's going to train it up for a little bit. It's going to take a look at all of those data, kind of plot them out, figure out where the boundaries are between all of these different movements, and then figure out a mathematical way to figure out, I have this electrical signal, what is the person trying to do? And then work backwards from that and then tell, yeah, happy sound. So open, close, and now I got the rotate. Sort of. Close enough. You did good. You can go to sleep now. So again, not perfect, but we're starting to get closer. So now we have a way that without having to cycle through a whole bunch of options or remember some sort of like Morse code pattern to do the different movements with the hand, I can have them all accessible at the same time. And I can rotate my hand, open my hand, do something with my wrist, pick up an object, rotate the wrist again, all kind of seamlessly. Still segmented, but more seamlessly than before. What happens if we're dealing with somebody with a higher level amputation? Somebody like a shoulder disarticulation here, for example. There's no muscles that the nerves are going out to, so the nerves are still firing. They're still sending signals out from the brain. What can we do with these signals? Well, there is a surgical technique that was developed by Dr. Todd Kuiken from our lab back in 2003. It's called targeted muscle reinnervation. What you do is you take the nerves that used to go out to the extremities, the now missing portions of the limb. You grow these you kind of attach them to muscles that still exist, muscles that aren't doing anything. So for the example of a shoulder disarticulation individual, for example, the pectoralis muscle right here on the chest does this movement. There's nothing to move here anymore. So this muscle is just kind of hanging out and not really doing anything. So they took the nerves that used to go down to the elbow, used to go down to the hand, used to go down to the wrist, grew those into the pectoralis muscle on the chest. And now when the brain sends a command to flex the elbow, the chest muscle will contract. The nerve doesn't care. It's just like, I have a home now. It's this muscle that I'm in, and it's just going to make that contract. Doesn't matter like what muscle. It's not like, this isn't my original bicep. So this is Jesse Sullivan. He was a lineman. He was working on power lines. He is the first individual to have targeted muscle reinnervation. He was working on power lines and he accidentally crossed two leads and he lost both of his arms at the shoulder. He came in around 2003-ish, I think, and he had targeted muscle reinnervation surgery done on him. So what this means is that there's this video here. I love it because people kind of get squeamish a little bit. Not in like a bad way, but he's trying to flex and extend his elbow like this, and his chest muscle is contracting. I don't know about you all. I can't do that. I've tried. I can't do this. So you have these repeatable chest contractions. Put some electrodes on those. Teach a computer to recognize these chest contractions. All of a sudden, you have a very complex prosthetic device that does shoulder movement, elbow movement, hand movement, wrist movement, and you can control all of these at the same time. So on the left is Jesse, showing off this prosthetic device. On the right is Claudia, same thing. She had targeted muscle reinnervation surgery. And again, what you'll notice is that everybody's able to do these gross movements. You can like reach out in a straight line rather than like, all right, shoulder, elbow, hand. You're kind of able to do all of these movements at the same time. So this is really, really fascinating, and it has a lot of benefits. Since then, it's been done, I think, a couple hundred times on different individuals. We've started doing targeted muscle reinnervation. I say we, I'm not part of this. I just get to present the other hard work that people do. Targeted muscle reinnervation has been performed a couple hundred times. It's been done on shoulder disarticulation individuals, those with transhumeral amputations. I think we're gearing up to do some transradial. We've done a couple of transfemoral. It's a really, really interesting surgical technique, and it has a lot of benefits. One of the other benefits kind of came as a surprise. So when Dr. Kaiken was kind of touching around on Jesse's chest to see how things are healing up, Jesse said, "I feel my elbow," or "I feel my hand." Turns out the nerves that grew into the chest muscles also grew into the skin, and he started regaining like skin reception for the now missing limb. So there were parts of his chest where you could touch it and he would feel the back of his hand, or he would feel his elbow, or he would feel his forearm or his fingers, which is incredible because now you have a potential way to, for example, like you said, I can put some sort of force sensors in here and I can feel how hard I'm pressing on something. Or I might be able to feel temperature, or I might be able to feel like if I'm bumping into something, things like that. Which is, I love this story because it's one of those happy little accidents that, yeah. It's one of the, I wonder how long I'll be able to use this joke before nobody gets it anymore. It's one of those happy little accidents that you weren't expecting, but it turns out it's really important. Not just for the ability to feel the missing limb, But also, I think people are working on doing some research in this area, but it seems that having these sensations of the missing limb, even if you're not using them to control a prosthetic device, can help with phantom limb pain. It can help people get rid of or not develop phantom sensations or phantom limb pain. Phantom limb pain, for anyone who's not familiar with the term, it's a pain of the missing limb. So a lot of people will describe it as like their hand is kind of contorted in an uncomfortable or painful way. And what's unfortunate about this is that there's not a lot that you can really do. You can't uncontort the limb because the limb is not there. So you're almost like at the mercy of, it's sort of a brain condition almost of, it was expecting sensations, it's not feeling anything, what do I do? Maybe I'll make something up. There are certain therapies that you can do. One of the most common is mirror box therapy. So if I place a mirror right here in the middle of my body, I place my amputated limb over here, I place my sound limb over here, and I look on this side of the mirror. Because I have the sound limb over here, it looks like I'm seeing that reflection. So it looks like I have a sound limb on this side, and our brains are kind of stupid. If you show it something, it's just like, oh, it's fine. And it'll just like, for a lot of people, the pain will go away because you just show it like, oh, the hand is there. It's, I don't know why I was, never, I'll stop. Whatever it is, like our brains are really, really easy to trick in that way. And the mirror box therapy is a really great way to take advantage of that for therapeutic benefits. So we've been talking a lot about upper limb devices, but more recently our lab has extended into myoelectric legs, robotic legs. The one that we're showing off here, for example, is one that's developed at Vanderbilt University. It's a robotic knee and ankle. Again, one of the challenges for prosthetic legs is that there are a lot of different walking types that you have to do. You're walking on level ground, that's pretty easy. But if you're walking up or down a set of stairs, that's more challenging. And even ramps, you might not think about it, but if you're walking up a ramp, it helps to have your prosthetic device inject energy into you walking up that ramp so that it helps you kind of glide up. And if you're walking down a ramp, you want it to absorb a little bit of energy so that you don't like kind of careen forward. So again, we have this robotic leg. We need to figure out ways to get it to do what we want, when we want. How do we do that? Turns out you can use that same sort of framework for legs as well as hands. So we can train a computer to recognize what it looks like when an individual is walking on level ground or walking up or down a set of stairs, not only from the electrical signals that are coming from their residual limb, but also from some of the sensors that are on the leg itself. So for example, foot sensors or gyrometers that are showing where the leg is in space, things like that. You can take that information, show it to a computer, say, hey computer, figure out what each of these different walking styles looks like. And when you do that, now you have a system that can dynamically walk up a set of stairs, go to level ground for a little bit, switch into a ramp descent where it's absorbing some of that energy. When he's down at the bottom of the ramp, it'll recognize that he's at the bottom of the ramp, switch back into a level walking mode, all without having to, for example, right? So it's like the phone thing is an option if I'm like at a staircase, for example, but it's not ideal. I don't want to have to pull out my phone. This offers a sort of seamless way to transition between these different types of gait patterns. All right, had enough puppy break? Cool. We also do a little bit of mechanical design in our lab as well. So this is a device that we call the RIC arm. One of the problems with prosthetic devices is that they can be very big and very heavy. An example that I like to give is if you imagine, let's say I was 200 pounds. I'm not. Let's say I was 200 pounds though. If I was like average proportioned 200-pound man, from here down, my leg weighs 32 pounds. If I had a prosthetic device that weighed 32 pounds, it's the exact weight of my missing limb, and I put that on me, that is a 5-year-old child hanging onto my body and pulling straight down. Right? Not ideal. So we tend to not really think about how heavy our limbs are because they're attached to us. But for prosthetic devices, you want to make these devices as light as possible. Even going like beyond the weight of the missing limb. So prosthetic devices are often large, they're often heavy, which creates an unfortunate precedent where a lot of women are too small to use the prosthetic devices that are out on the market. Most prosthetic limbs are fit or sized for the 50th percentile man, which means 50% of men and more than 50% of women, this device is too large or too heavy. So we designed something that's a little bit smaller. It fits the 25th percentile female. So now you have like about 87% of people that this device is going to fit. So on top of all of that, we tried to cram as much functionality in here as we can. We used 3D printed plastic to kind of reduce some of the weight. But we fit, how many controls do I have on here? 5 different degrees of freedom on this hand. So you have an elbow up and down, elbow flexion extension, fingers open and close. Everyone loves that one. Wrist rotation. And then you also have wrist flexion like that. And then you also have different thumb movements here so that you can grasp objects in different ways. So this is our attempt at making a device that is compact, it's lightweight, it's small, but it still has a lot of functionality. And again, I'll let you all play with this a little bit at the end. I'm being told that I am slow and that I should go faster. Pretty typical for me. So I'm going to run ahead and go to the next slide. But one of the advantages of this device is that it's capable of doing more than one movement at a time. So for that robotic hand here, you can open and close the hand, you can rotate the hand, but you can't do both at the same time, which is fine for most conventional control because a lot of conventional control doesn't allow you to mix 2 different movements into one control output. But the work that we're doing in our lab allows us to do that. We're developing ways to allow people to do multiple different movements at the same time. So the robotic hand here, for example, is going to like rotate and close the fingers and flex the wrist out, all at sort of the same time. I mentioned exoskeletons before. We're not developing any exoskeletons at the CBM, but what we are doing is we're evaluating exoskeletons. Exoskeletons are kind of new in the medical world, and what that means is that we don't know how to evaluate them. How do I show somebody that an exoskeleton provides a benefit? Do I show that it enables them to walk faster? Do they walk farther? Do they walk with a lower metabolic energy? Like, how do you show that these exoskeletons are beneficial? So we're working with a lot of exoskeleton manufacturers from Honda, from Rewalk, and from Exo to take their exoskeleton devices and test them with their intended population. So that's typically somebody with a spinal cord injury or somebody who has had a stroke and has hemiplegia, for example, and needs a little bit of like kind of unilateral assistance. So that's some of the work that we're doing with exoskeletons.
Are you doing any like measuring oxygen consumption or?
Yeah. So that falls into metabolics, and that is one of the things that we're looking at.
Ripley with the loader.
More recently, we've also put in, we've come out with a design for a wheelchair. So I have the promotional video kind of playing in the background here. This is a really, really cool wheelchair design. So one of the things about wheelchairs is that you're almost always kind of like down here, de-elevated, which means a couple of things. On top of being unable to reach things on high shelves, stuff like that, if I'm talking with an individual, that individual in a lot of cases is literally and sometimes figuratively talking down to me because I am at this level. So what we did, we designed a wheelchair that has both kind of sitting and standing capabilities, and it allows somebody to actually move around in that standing position. So you can use it as a normal wheelchair as you need to, but you can also, I'll play it again from the beginning just real quick. You can also elevate yourself, bump up into that standing position, and it allows you to have eye contact conversations with individuals at their same height, but also provides benefits of, for example, being able to reach things that were not designed accessibly. Really, really cool design. I don't have it with me, but it's a very cool design.
I have seen power chairs with a lift in them.
Mm-hmm. I've seen power chairs with lifts in them. A lot of times, I've seen, for example, mechanical wheelchairs that allow you to move into a standing position. What separates this one out is that you're able to move around in that standing position. And all of the mechanical chairs on the market, and I think a lot of the powered wheelchairs on the market, don't allow you to move around while you're elevated. So this is a little bit different because it allows for that.
The one that I've seen, it's a science fiction fan that we run into at World Convention.
Okay.
That it's kind of, it looks kind of like a barber chair.
Okay. Yeah, I've seen the ones that like.
She's still seated, but she can be at different levels.
Yeah, and one of the other benefits of being able to even not necessarily stand up, but just like elevate, move at different levels, is that it shifts your weight around in your chair. A lot of individuals who are in a wheelchair will develop blood clots from not necessarily moving around a lot. Being able to switch from that seated to that standing position goes a long way to improve circulation in the lower extremities.
Also the spine.
And the spine, yeah.
Spine only sits all the time.
You have spine.
Problems.
Yeah, and there's a lot of ulcer issues, especially with seating, for example, that you can alleviate some of that by being able to shift that weight around and move into a standing position.
Good for the heart.
Yeah.
To move back and forth.
Yeah. So it's a really, really cool design, and I'm glad that it seems to be getting traction. That wasn't supposed to be a pun, but one of the other things that we're doing a lot of software development. We're trying to implement, I know I was bashing smartphones for like the last hour or however long I've been talking, but we are actually trying to implement smartphones into some of the things that we do. So one interesting study that we're doing right now is we're trying to collect information from individuals. I know that sounds evil. We're trying to collect movement information from discharged patients to ensure that they are how am I trying to say this? To ensure like community mobility, for example. So when you're working with a patient in a hospital, you can kind of monitor what they're doing. You can see how well that they're moving around. You can, as a clinician, you can tell them like, let's go for a walk here, or let's go to this place, or something like that. As soon as they go home, blindfold. Like, we have no idea what somebody's doing when they're at home. So if you say, all right, do this exercise every day. I want you to be, getting out. I want you to, do all of this stuff, and I'll see you back in 6 weeks. The only way you know what they've been doing is to ask them 6 weeks later, how have you been? And a lot of people say, great. But that's not always like a good way to show that these interventions are beneficial. So we're working on developing some smartphone apps that will actually, they'll collect all these different measures of like what activity somebody's doing. If they're walking, sitting, climbing stairs, but also combine that with some GPS information to see like, are you mostly hanging out at home, or have the interventions that we've been doing helped people get out and participate in social activities outside of the home, which is very much a quality of life sort of measure. So it's another one of those kind of interesting sort of outcome tools that's being developed at the lab. Last section. Where do we go from here? I know that like a lot of the stuff that's here is really, really cool. And like I said, a lot of people have put time and effort into creating these devices and creating these controllers and doing all of this work. But we still have a long way to go, which is good for me. So that means I have a job. But there's still a lot of work to be done, for sure. If we're talking about exoskeletons, for example, one of the things about these exoskeletons is the way that they are controlled. You currently, anybody who's using one of these exoskeleton devices, especially for a spinal cord injury, for example, these patients will typically have a set of crutches that they use. And the way the exoskeleton knows, do I take a step forward, is you lean forward with one crutch and kind of touch the ground. There's a little sensor on the crutch. Exoskeleton goes, oh, okay, and then takes a step forward. And then you do this side, take a step forward. Do this side, you take a step forward. So that is not an ideal solution. But what's also not an ideal solution is like the robot trousers. I see a couple people who recognize this. That's good. You don't want the idea of this exoskeleton where I just say, like, take me to work, and then just kind of like walks me off to work. I think some people say like, yeah, that sounds cool, I want that. But it's the same idea with like autonomous cars. People are like, I don't want a robot to drive, I want to drive myself. I want to feel like I'm in control. So you have to find something that's in between like robot trousers and like crutch control. So we're working on a couple of things in our lab, ideas of how to collect information from the individual to figure out what it is that they're trying to do. Especially if we're dealing with, if we're working with a like a hemiplegia patient, for example, who still has some level of volition of the lower limb, trying to figure out like, are they trying to take a step forward, and then helping them take that step forward, not necessarily being like, oh, okay, time for me to take over, doing that sort of thing. So there's this balance for exoskeletons. That's going to be really interesting to see kind of what happens with that going forward. For prosthetic devices, there are a couple of things that I'm really excited about. That's Nicole Kelly in the middle. She has a YouTube channel where she kind of shows off these prosthetic devices, and like, she's not afraid to show things like they don't work sometimes. The two things that I am most excited about to see for prosthetic devices, one is sensory feedback. So on the right is a gentleman who has actually nerve implants that stimulate the nerves in his residual limb. And when you stimulate these nerves in just the right way, he actually feels different sensations on his missing limb. It's kind of interesting because they don't know, they haven't figured out how to code like, all right, you're pushing on a hard object. All right, you're pushing on a soft object. They just try different things and then he says what it feels like, which was unfortunate for him because they were trying a bunch of stuff. This is out at Case Western Reserve University. And they tried one thing, and the guy who was running the study said, all right, what does that feel like? And he's like, that feels like cotton balls. I hate the feeling of cotton balls. I hate cotton balls so much. And he basically threatened, like, don't ever do the cotton ball feeling to me again. Never do that to me again. So like, just by pure happenstance, they found the cotton ball like feeling combination of senses. But sensory feedback is really, really important, not just for being able to feel like, is there an object here, or is this object soft, but also there's a sense called proprioception. To illustrate proprioception, I want you all to take your finger and kind of hold it out here, just like this. Now close your eyes and touch your finger to your nose. How did we do that? There's a sense called proprioception, which is your brain's idea of where your limb is in space. We have that. Prosthetic devices don't. The only way for us to know what a prosthetic device is doing is to look at it and see what my hand is doing. You can also you can hear the motors and stuff like that, but you're pretty much limited to those two things. So developing sensory feedback that allows you to feel things and know where your limb is in space, those are going to be two things that are very important going into the future. The other thing on the bottom left, you'll see a very confusing image. There's a technique called osseointegration, which is where you can actually have titanium implants inside of the bone. And these implants stick out a little bit, but you can attach the prosthetic device directly onto that implant. What that does is that alleviates that 5-year-old child hanging onto your leg problem, because now the device is directly connected to you instead of suspended holding onto the outside of your skin and kind of pulling down. So it has a lot of benefit for helping alleviate the feeling of weight and helping people embody their prosthetic devices a lot more. And then on the top left, there's a company that spun off from the Center for Bionic Medicine. It's called COAPT, and they do a lot of machine learning and taking the the machine learning aspects and trying to actually commercialize it so that people outside of the lab, individuals who actually need this technology, can use it. So you're going to start seeing a push towards that commercialization as well. But ultimately, it's just going to be pushing more and more towards these things, getting individuals, making it easier for them to do these daily activities, these activities of daily living, being able to do the things that they love, being able to not be hindered by their limb difference, but to be able to participate fully in society. And I hope that's my last slide because that sounded really final. It is. We get a lot of funding from the National Institute of Health and also from the Department of Defense. But of course, the work that I presented here is mostly not mine. It's a lot of individuals who put hard work and many years into this stuff. So of course, big thank you to them. And now, last slide. So I will take questions for however long people have questions. Yeah.
First, if you go back to the mechanical control of the hand, naturally there is a battery that is being discharged. So doesn't it sometimes hang up
For this one?
in the air? No, the one that's
Oh, for this one. Yeah. So battery power.
mechanical devices are battery operated or energy use.
There's an interesting.
Then it's an exoskeleton. Same
Yeah.
thing. A person can just freeze.
Yeah. So there's a fundraising event that we do as the AbilityLab. It's called Skyrise, and we climb the 103 floors of the Willis Tower / Sears Tower / are they renaming it to something? Or no, that's the Hancock Tower. Hancock they're renaming. This is the Sears Tower, the Willis Tower. We climbed the 103 floors of that, and instead of running a 10K or something like that. One of the years we had one of our patients climb those 103 floors with the robotic leg. We had to carry 3 extra batteries with us to do that. So batteries are a big deal, as well as heat, for example, things like that. And those are, for a device like this, I think you can generally get, I'm gonna like roughly ballpark here. I think you can, if you're using it a lot, you can probably get around 4 hours of use with a hand like this. But the way that these hands work is that they have interchangeable battery packs. So you can carry a couple of extra battery packs with you, and if your hand is starting to run out of power, switch it out, put a new one in. That is a problem, for sure. And you know, you have this other sort of trade-off of, oh, I could shove a big battery in there, but now it's like really heavy. So everything comes with a cost. You know, you're starting to see more battery technology come out that can get more power into a smaller space. I'm not an expert on that, but for sure, if it's cost effective, you're going to see that technology getting implemented more into these prosthetic devices.
One more.
Yeah.
All of these devices, let's say mechanical devices, mechanical engineering devices, would go away if you could just regrow a limb. Where do we stand on making progress there?
I tell people that we're gonna be regrowing limbs before we are fully replacing limbs with robotic technology. Because, so you remember that first 5 minutes where I was just like, the body's amazing, there's a lot of stuff. Regrowing limbs is a little bit of a black box sort of thing, where it's just like, if you can get it to happen, we don't really care how it happens or how it works. If you get it to happen in the first place, like if you get the biology to communicate with itself and restructure itself in that way, you know, that's had millions of years to figure that out, and we've only been working on trying to figure out how humans work for maybe 500 if you're being lenient. Like, so I think prosthetics is sort of a merging of two separate worlds, whereas regrowing limbs is like, it's all one thing. It's this uniform idea. Everything is you, in a way. So I think we're gonna be regrowing limbs before we fully, perfectly replace biological limbs with robotic limbs. That said, depending on how much of a transhumanist you are, there's still benefit to working with prosthetic devices if we're talking about human augmentation, for example. A lot of that tends to happen more with exoskeletons. For example, the Army's working on exoskeletons that allow their soldiers to carry more weight, and it'll take the weight from the backpack and load it directly into the ground through like an exoskeleton frame. The big one is Japan has a company called Cyberdyne, I know, that developed a exoskeleton called HAL, I know. This company is not, I don't know who chose all of the like evil, like if their CEO is like Sauron or something, I wouldn't be surprised. But this is an exoskeleton that can actually offload weight through the exoskeleton itself. So you started seeing it with the Fukushima meltdowns, the nuclear reactor meltdowns and the tsunami a couple years back. They outfitted individuals with these suits to help kind of clear some of the rubble and like basically, you know, A, not strain themselves, and B, augment human strength with robotic strength. So you're going to be seeing...
Read Heinlein's book, Starship Troopers. Or have you?
I need to. Yeah.
So the proprioception, do you know a little bit about where that comes from? Or is it muscle? Is it, how does
Yes. The answer is yes to all of the things. So this is the research that I'm doing. So the one thing that wasn't in the presentation is the research that I do. Proprioception is thought to be, you have a lot of different sensors in the body. In the muscles, you have muscle spindles, which determine muscle length, like how long the muscles are. but you also have Golgi tendon organs, which tell you how much force the muscle is applying. On the skin, you have stretch receptors, which tell you how much your skin is stretching. There's also some receptors in the joint. So your brain kind of takes inputs from all of those and combines them to figure out where the limb is in space. This is a field that's called motor learning, and it's kind of, if you imagine somebody trying to learn how to play tennis, you hand them a racket and you tell them to swing it, and they're like, they don't really know what they're doing, but they took a try, the body compared what it thought was going to happen to what the signals in their body told them actually happened, and they're like, all right, that wasn't quite right. Let me refine that plan and let's try it again. And then you take that error compared to what happened, refine it again. And that's why as you continue practicing tennis, eventually you get better, you get more repeatable, you know what it is that you're doing. And it's because your brain has now developed a model, an idea of what muscle movements are required to do this like limb output.
It's kind of like a supercomputer version of what you were doing with a hand.
Yeah, in a way. The brain's confusing also.
Yes, remembering that an iPhone beats the heck out of the supercomputers we had in the 60s.
So where's the neural part? I mean, the title is neural.
I didn't choose the title.
Huh?
I didn't choose the title.
Oh, you didn't? Because I'm like, neural networks is a big thing.
Yeah, for sure. We have looked at, there's a lot of different machine learning algorithms that you can use to like go from muscle output to like the thing that somebody's trying to do. Neural networks are interesting as a machine learning algorithm because they're really smart in a way, but they're also really dumb. A neural network can learn a pattern really, really well, but if that pattern doesn't generalize to all of the possible things that you could do, it's going to make really strange decisions as soon as you move outside of the data that it learned. So if you imagine like computers looking at pictures of letters and numbers, for example, and you give it some 3s and you give it some E's, that's kind of the classic example. And you're like, all right, I've learned that like a 3 points around this way and an E points around this way. Okay, I've learned that. And then I give it a Q. It has no idea what to do with this Q. So that's the complexity that you run into with neural networks, is that a lot of times, unless you train them properly, they don't generalize. The thing about the title for the talk, it is actually, to whoever came up with the title, I apologize. I'm not trying to be mean about it or anything if they ever watch this. One of the kind of pet peeves that we have in our lab is the term brain-controlled prosthesis, because what does that mean? I am brain-controlled. Am I a brain-controlled? Like, so what we're trying to do is we're like as non-invasively as possible, we're trying to find really, really strong ways to take the intent of the user and transition that to the robotic hand. So you can do that by going directly into the brain. You can do that by connecting directly to the nerves. You can do that by recording directly from the muscles inside of the body. We choose to take the approach where we look at the muscles, the electrical signals we get on the outside of the body, and see what we can do with that, because that is that's the kind of cheapest, least invasive, and most accessible way to get that. Did you have a question? Yeah.
Why did your prosthesis completely spin around? Because our wrists don't completely spin around.
Why not? If your wrists could, would you do it? Like, There's a video of a guy, another Iraqi veteran, who has one of these hands, and he's holding like a chicken drumstick or something, and it's just like turning around in a circle, and he's like, "This is great. It's just like a rotisserie." And he just takes a bite out of it every time it comes around. Like, I think it's because it's that, like, limiting the rotation is a limitation that doesn't benefit anything. So you could put it in for realism, and individuals are going to try and orient their hands the right way because it looks more cosmetic. But there's no real benefit to limit the amount of rotation that you can have. I think probably one of the other advantages of that is that the way that you put the hand on, I can put it on in any order. There's not like a tab where I'm like, I have to align the hand and then put it in the proper way. The way that these work, I can just pop it in anywhere and rotate it where I need it to go. Yeah.
So I have a question because I used to go to RSC as a kid.
Okay.
And one of the things I remember when I was there was everything was flesh color. All the prosthetics, you know,
Mm-hmm.
it always made the look as realistic as possible.
Yeah.
So I'm just curious, like, do you see more people going for the more like utilitarian or like robotic looking, or are still people like going for like the cosmetically good?
It depends on the individual. There was a misconception for a while that women tended to be more concerned with cosmesis, how something appears, than men. Turns out that's not the case. But it depends a lot on the individual. If somebody's like really big into like cyberpunk sort of thing, like they'll go with, they probably already decked out their prosthetic hand with all sorts of cool stuff on it, right? But that's the reason why that's the reason why a cosmesis exists, a cosmetic prosthesis, is because some individuals, literally all they want is to not be noticed. In that way, in that particular way. But it depends on the individual. Some people are self-conscious about limb loss or limb differences or things like that. Other people are like, "Hey kid, check this out," blah, like that sort of thing, right? So it all comes down to the individual, and that's why it's so important to, when working on prosthetic devices, to work with the individual and work with clinicians whose entire job is to know what people want. Because it's like that remote control analogy. Like the engineer will be like, I'm gonna make this like jet-powered prosthetic foot that does all these things, and somebody's just like, I just need to get to the bus, man. It all comes down to the individual. Are we still good?
Somebody else?
Okay, go ahead.
Since you took out your cell phone, press 1, press code 2, 3, or 4.
Mm-hmm.
In our world, everything is Wi-Fi, Bluetooth.
Yeah.
Have you researched anything communication-wise? Hey, I'm going to go walk up the stairs. So a receiver would tell.
So that is actually a really interesting point. I might have a slide. No, I think I took it out. This is kind of fun, but I'm going to go back to that slide. If we were talking about brain-controlled prosthetic limbs, I'll play this real quick. This is a woman who has brain chips. She's quadriplegic spinal cord injury, high level. So she's using literal brain signals to control a robotic device. I have this in here in case people ask about that kind of stuff. But I'm going to go back to this slide here. So camera guy, I promised I wasn't going to stand in front of the thing. I'm going to break that promise. It's really hard to read these things on the bottom, but there's a button down here that says proximity control. iLim has a series of RFID chips that you can stick on things around your house, and when you're near those things, it'll recognize the type of grasp that you want to do. So if I'm near my cupboard and I'm trying to grab a glass, I can put an RFID chip near my cupboard. And when my prosthetic hand is near that, it'll recognize oh, you're probably trying to grab a cup, and it will choose that grasp that you would use to grab a cup with. So there is stuff like that out there. Now, one of the other things, one of the grad students in our lab is also working on incorporating vision systems with prosthetic devices. The idea is that the signals that we give off are changing all the time. You saw that earlier when I tried to put the hand back on and it didn't work. But the environment generally is steady. So what she's doing is she's taking like almost like a Kinect camera. You can put it like on a little belt pouch here, for example. And while you're walking around, the camera will look at the environment and figure out, are you walking on level ground? Are you walking up or down an incline? Are you approaching a set of stairs? And when the camera detects that you're about to come to a set of stairs, it'll signal to the prosthesis, the prosthetic leg, hey, it's stair time. And then it'll start and walk up the stairs like that. So we are trying to incorporate that kind of external information as well.
I was alluding more to voice control through the smartphone.
Oh, okay. Oh, like a go-go gadget, like Inspector Gadget sort of thing? Like go-go gadget hand twist. So, we haven't. I wouldn't be surprised if there's some research group out somewhere that has looked into that. For prosthetic devices, I don't think that would particularly catch on, because if we're talking about trying to, someone with a prosthetic device trying to be kind of be low profile, for example, and now they have to like kind of tell their hand like rotate or this or that, or whatever. For a prosthetic hand, I don't know how much traction that would have compared to other, like just pressing a button on a phone, for example.
But you tell the phone, I'm going to grab this cup harder, lighter. Tell the cell phone to do it, to communicate to the receiver.
That's interesting. Yeah, I don't know anybody who is who's looking into that for sure.
With any mechanical controls, then, with the exception of your voice.
The difficulty there is that, so if you're getting rid of all the mechanical controls, all of the electrical signals that we're using to open and close hands, for example, so the trick there especially comes in if you're trying to do simultaneous movement. So if I'm trying to like move my elbow out this direction and also extend my wrist back and open my hand all at the same time. With some of the machine learning stuff, we're getting better at it. We're still not quite there, but we're getting better at doing that. Like you saw, almost there. Yeah. Oh, that's... Yeah, so you saw Jesse here is able to do all of these large movements that involve almost every joint of the arm at the same time. If you were doing voice control, you might have to say like, okay, elbow up this many degrees. All right, elbow down this many degrees. Hand open this many degrees. And it becomes this sequential... The cognitive load starts to get a little bit higher as you have to now parse out in your mind, what movements do I want the hand to do and what order do I have to tell the hand to do it? Yeah.
When you were talking about direct brain control, like having implants, that I was thinking about non-invasive EEG. Like, is that something that is actually being
So,
or is that just out?
it is being used in a couple circles. That was actually my undergraduate senior design project, not for prosthetics, but for a wheelchair.
You use an emotive epoch?
We did use the emotive. Turned out my eyebrow signals were way stronger than my brain signals, so I drove a wheelchair with my eyebrows instead.
So the MYOELECTRIC.
So MYOELECTRIC, yeah. There was again, the thing with, so EEG, for example, there's a very clear benefit of using that for someone in a wheelchair, someone with high-level quadriplegia who has no other outputs. That is a very clear example. But again, going back to earlier when I said that, relatively speaking, an amputation is somewhat minor, it's because there are a lot of other avenues that you can use to get something done, even if you have no prosthesis. But if I have a prosthesis, you have to, the trick with EEG is that, to my knowledge, it's not particularly repeatable. If somebody's just like, ooh, a squirrel, like different brain signal all of a sudden. There was a talk that I heard maybe back in like 2014 or something like that. Somebody found out that people who do meditation are better at EEG control than people who don't meditate, which is kind of interesting. But yeah, for EEG, it's an option for sure, but I think there are more repeatable and more accessible options that require less brain training that somebody would want to go through before going to like EEG.
I saw someone used ultrasound on the limb. Have you seen that one?
I have, to control the limb?
Yeah.
Yeah, I think I have, because then they're looking at like the muscle, the individual, like the muscle fibers and the individual muscles themselves. So that's an interesting option. There's also something called MMG, which is mechanomyography, and that's literally putting a microphone on your arm and listening to the low frequency rumble of your muscles contracting. So it's just like that sort of thing. And it's supposed to be a little bit better than EMG. And there's a postdoc in our lab who combined an EMG sensor and an MMG sensor into one package so that you can extract both. So there are people looking at all sorts of different ways of collecting that information. There's people looking at different ways of giving that feedback back out, for example. Like, do I put a little like rumble tactor? Do I stretch the skin? Do I put it on the arm? Do I put it on the back? I'm doing audio feedback because people can't get that wrong. It gives me the best results. So there's a lot of options. There was a period of time in like 2014 where almost every paper coming out in prosthetics, or at least like the machine learning thing, was just like, we tried this new algorithm that gave us like a 0.5% better improvement than the other one. And then that died out after a while because people were like, all right, we get it. There's different, like you could do a support vector machine, you could do a neural network. We got it. Do something more interesting, please. Was there a question? Yeah.
Last one. How
You
does
said that last
Stephen
time.
Hawkins, being fully paraplegic, how does he control his voice? Can't detect any motion whatsoever in his neck.
I think, if I remember correctly, I think he has like a sensor here and he has like an eye twitch that he can use to cycle through. I'm pretty sure, I'm not a Stephen Hawking expert. I would have thought that he has movement of his eyes. So he could potentially be using eye tracking software on that monitor as well. But I definitely have seen in interviews, like there tends to be a sensor that's kind of right here picking up signals from that. And using Stephen Hawking as an example, going back to that discussion about the question you were asking of whether people want like prosthetic devices that look very lifelike or don't, Stephen Hawking has gone on record of saying that he doesn't want a more realistic like text-to-speech operator, because that is his voice now. And regardless of how real or not real it is, that is his. And that's how people perceive him, and that's how he perceives himself. It's this like personal decision sort of thing.
one comment on that I've noticed that he obviously stores up a sentence.
Yeah.
And it probably takes, depending on how much and complicated, it may take a while for him to input, and then it comes out
Yeah.
at normal speech rate.
Yeah, it's. I've seen interviews where he's given the questions weeks in advance so that he can prepare the answers, and then during the interview he can just kind of program it out. I think he also has a pretty big bank of commonly used words that are readily accessible, and then if that's not there, then it goes to like a letter switch. And has anyone ever seen how eye tracking software for spelling works? It's literally, it's a, look at that, a whiteboard. It's like, you have a whole bunch of circles that are like this, and these are like letters A through G, and then this is like H through, you know, whatever. And you go like that around the circle. So the first thing that somebody does is they choose the first circle that has the letter they want, and then from there, it goes out and they have like another set of letters that have all A, B, C, D, E, F. I know what I'm doing. So it's really interesting. It's like, it's relatively, it's a fast way to get access to all those letters pretty quickly. Anyone want to play with some toys?